chemistry, starting with atoms. Okay, so we already talked yesterday. You know that the nucleus of an atom has protons that are positively charged and neutrons that are neutral, and then floating around outside in an orbit or in a shell would be the negatively charged electrons. Okay? So atomic number. Each chemical element contains a specific number of protons, and this number is the atomic number. Okay? So when we're talking about the atomic number, we're looking at the number of protons. Now remember that I told you for something to be an atom, the number of protons has to equal the number of electrons, which means that atoms are overall zero charge. Okay, so if we look at hydrogen in this picture, hydrogen has one proton here and one electron. And so you can say that hydrogen is definitely an atom because the number of protons and electrons equal. Look at helium, 2 protons, 2 electrons. So this model right here would be considered an atom because the number of protons and electrons equal each other. Now there's one other thing about atoms that you should be aware of, is that atoms like to be stable. And if you look at the atom that I drew here, okay, it has one valence or one shell or one orbit. And the maximum number of electrons in this one orbit is how many? The first orbit. 2. Absolutely. If our atom has 2 electrons in this orbit, and it's the only orbit it has, this is now considered a stable atom. Now, stable atoms, one of the things you should know also is they don't bond to anything else. They just stay by themselves. They're kind of little hermits. They don't like to bond to anybody else. They're just nice and stable, and you leave them alone type of thing. If we only have, let's say, 1 electron here, okay, is this now considered stable? No. No, absolutely not. And what this means is that this atom, although it's not stable, it likes to bond to other things because it wants to become a stable atom. And I'll show you how it can become a stable atom in just a minute. But all atoms have like this drive to become stable. Now, if we had 2 orbits, we can then put 8 electrons in this outermost shell or valence. And now our atom also becomes stable because we need 8 for stability. Okay? If we have more than 2 orbits, if we have 3, 4, 5, an atom can be considered stable as long as it has 8 electrons in its outermost orbit. And this is typically what's referred to as the octet rule. Okay? So we're looking to try to get 8 electrons in the outermost orbit to allow the atom to become more stable. So look at lithium. Is lithium in this picture considered an atom? How do you know it's an atom? You've got 3 protons and 3 electrons. They equal each other, and so you can consider this an atom. Is this a stable atom? No, absolutely not, because it only has 1 electron in its outermost orbit. What about neon? Is this picture of neon an atom? Yes. Yes, because it has 10 protons and 10 electrons. Is it a stable atom? Yes. Yes, absolutely, because it has 8 in its outermost orbit. Okay, now, if we change electrons up a little bit so that the number of electrons do not actually equal the number of protons, we now would refer to this atom as an ion. Ions are where protons and electrons actually do not equal each other, okay? And we'll talk about what that's all about. We're also going to talk about ionic bonding, covalent bonding, and hydrogen bonding. We're going to go over these three types of bonds. And this bonding is what helps to make atoms stable. They form bonds with other atoms to get that stability going on. Okay, so if we have an atom that becomes an ion, and we have more electrons than protons, we'll have a negatively charged ion. We call that an anion. If we have an ion that has more protons than electrons, we'll have a positively charged ion. We call this a cation. Okay? So let's go over how this all works real quick. If I say to you that the drawing I just made is an atom, can you tell me how many protons this atom has? Yeah. All you have to do, absolutely, is count the number of electrons. Because if I tell you this is an atom, you already know the number of electrons has to equal the number of protons. So just count the number of electrons. We know there's 17 electrons, so there'll be 17 protons. So we have 17 electrons, 17 protons, and if you remember I told you atoms have to have an overall 0 charge. So this would be an atom for sure. Okay, let's try another one. Does this atom have? It has 11, exactly. So we have 11 protons, 11 electrons. We have an overall 0 charge, so we know that this is an atom also. Really simple, okay? Now, next question. Are either one of these stable atoms? No, because they don't fulfill the octet rule. There's not 8 electrons in the outermost orbit. So in this guy over here, we're just kind of missing 1 electron there, right? And then we'd have 8. Because electrons, they like to float around in pairs, so that's why I've paired them up like this. Over here, we're really missing all these guys to have our 8 in the outermost orbit, right? So if these 2 atoms came together and they wanted to become stable, what could you suggest that they do with their electrons?
They could share, and then that would take, if that electron moved over here, that would take that outermost valence.
Okay, but that's not actually sharing. We wouldn't call it sharing. We would call it like giving away, like a present. So we take this electron and make it as a present for this guy. So now this guy has 8, and his whole outer orbit is gone. This guy has 8, yes? Okay, is there anything else we could do? Couldn't we also do this? Couldn't we take the 7 from this one and give it to this one?
No.
Why not? Why not? Couldn't we do it? I mean, what's the law against it? Okay, we could take the 7 from this one and give it to this one, and they'd both have 8, yes? Vice versa. You're looking at me like I'm crazy. I am, but not in this matter. We could do it. Now, of course, the reason you're looking at me like I'm crazy is because you've probably already been taught that it doesn't happen that way. But why doesn't it happen that way? Why not? I mean, it could.
Too much work. I guess it's
Too much work. Yeah, that's exactly right. Okay, so here's what I like to say. Mother Nature is lazy. Okay? She don't like to expend very much energy. She'd rather kick back on the beach with a Mai Tai. Okay? That's probably why she made beaches. All right? And so here's what's going to happen. All right? We're really only going to take this one and give it away over here to this guy, and now they'll both be stable. It could happen, and usually it's only going to happen like in the laboratory where we add a lot of energy to this and take 7 off and put it over here. It can happen, okay? But it doesn't usually happen in nature, all right? So if we take the 1 electron here, okay, and we're going to put it right over here. Now, this outermost orbit doesn't exist because there's nothing in it. So I'll just erase this. Okay, now look at what happened, though, to the balance between electrons and protons. This one over here has now an extra negative charge. So we really have an 18 here. And this isn't 0 anymore, is it? It's a -1. And this guy over here, we actually only have 10 electrons. So what's our charge over here? This is a +1. Okay? Now it turns out that this is sodium and this is chloride. And now our 2 ions, one has a positive charge, one has a negative charge. So you know opposites attract, right? So if you bring the sodium with the positive charge close enough to the chloride with the negative charge, these guys are going to bond. And what just happened, we just made a very nice stable molecule. Each of those atoms have 8 electrons in its outermost orbit. It fulfills the octet rule. This is a very happy, stable molecule. And chloride is our anion. Sodium is our cation. Any questions? I know this is quick. You've already had it in chemistry. You're all brilliant. Don't have to worry about this. By the way, this is just in your notes, a list of some of the anions and cations in the human body. We'll talk a lot about these first 4 here. Sodium, potassium, calcium, hydrogen. We'll talk a lot about chloride ions and bicarbonate ions. This is a big one in the human body, so we'll discuss both of these a lot, but I just wanted to put those in there so you could just sort of take a look. All right, let's quickly go over covalent bonding. Let me just take a second to erase all these. Now, ionic bonding is all about giving away or receiving electrons. Covalent bonding is all about sharing electrons. Protons do we have in this atom? 6. So this atom has 6 protons, 6 electrons. We know this is an atom because they equal each other and they have an overall 0 charge. Is this a stable atom? No, it's not. Because we're missing 4 electrons in the outermost orbit to make it stable. So what if I bring in a hydrogen? Our hydrogen has 1 proton and 1 electron. By the way, this is something you need to memorize. It's the only atom I'm going to ask you to memorize. I know it's difficult, but hydrogen has 1 proton, 1 electron. You need to remember that, okay? Think you can do it? Some of you look like maybe you can't. I don't know. Either that or you haven't had your coffee this morning, okay? All right, Starbucks on your way in. Well, you know. All right. I should have got stock at Starbucks. I'm gonna be here right now. Anyway, okay, so if we bring hydrogen close enough to carbon, what can happen to make both of them more stable? You have to be able to make both atoms more stable, because watch. If I took this one electron, this puny little electron, a poor little hydrogen, and I gave it to carbon, just like we did with the ionic bonding, would it make both atoms more stable? No, because carbon here might become more stable because now it would have 5 electrons in its outermost orbit, but look at hydrogen. It wouldn't have any electrons at all. So it would not become a more stable atom. Okay? So what do I have to do instead?
Add more hydrogen. Add more hydrogen.
Add more hydrogen. How the heck am I going to do that? How do I add this hydrogen to begin with? Let's start with adding this one first. Because they're not bonded to each other yet. They got to do something different, and I can't give away an electron to carbon. Or I could maybe take an electron from carbon and give it to hydrogen. Would that make them both more stable?
No.
No. Okay, now we got a problem. So what do I do instead?
Covalent bonding.
Okay, what does that mean?
They share their electrons.
Can share. So now, okay, you know that these electrons go around the atom. But when these two come close enough together, this electron can actually jump off and go around carbon and come back again. Now, electrons move at the speed of light. That's seriously fast. And so what this means is this electron, by the time it goes around carbon and comes back again, hydrogen never even missed it. Didn't even know it was gone. Okay? Now, if I'm going to take this electron from hydrogen and share it with carbon, it's only fair that carbon shares one too. So I'm going to take one of the electrons and I'm going to share it with hydrogen. And now, is hydrogen more stable? Yes, because it has 2 electrons. And carbon is actually more stable too. Not perfectly, but now it has 5 electrons in its outermost orbit instead of only 4. If we bring in more hydrogens, we can do it again. Bring another one over here. And do the same thing. We'll share electrons. And now we have an even more stable atom. Is this a perfectly stable atom?
No.
How many more hydrogens do we need to make it perfectly stable?
2.
2. All right, so let's put 2 more on here. Now, does everyone have, in this molecule, does everyone have the majority or the maximum number of electrons in its outermost orbit?
Yes.
Yeah, absolutely. So this is now considered a stable molecule. Okay, now you could draw it like this, all right? Or you could also draw it like this. And each of these lines represents the fact that hydrogen shared 1 electron with carbon, carbon shared 1 electron with hydrogen. Okay? So this would be considered a single bond. All right? Or you could, of course, draw it like this, just CH4. All right? Or you could draw it like this. This is methane. Now, there's 2 types of covalent bonding. There's a polar covalent bonding, and there's a non-polar covalent bonding. In polar covalent bonding, okay, both types we're doing sharing of electrons. But in polar covalent bonding, the amount of time that we share electrons between one atom and another is not equal. So one atom gets to keep the electrons for longer than the other one. In non-polar covalent electron bonding, it's an equal amount of time that the electrons are spent around each atom. And in this case, if you notice, the carbon is not a lot, well, and I didn't draw it super great, but maybe if you look at the overhead, you'll see it a little bit better. The size of the hydrogens and the size of the carbon is not much different from each other. So the electrons spend just about as much time around carbon as they do floating around hydrogen. So there's an equal amount of time that they share the electrons between each other. Whereas in the polar covalent, and I'll show you that in a minute, it is an unequal amount of time. Okay? So let's try another one. Okay, in the first atom, how many protons does it have? 6 protons. And in the second, how many protons does it have? 8 protons. Excellent. You guys are a quick class. I love it. Now, what do we have to do to get these two to bond to each other so that both atoms become more stable? Okay, so first look at it and ask yourself, can we give away or receive electrons to form an ionic bond and make them both more stable? Could we take one electron from this atom and give it to the other one and make them both more stable? No. And if you can't do that, you can't have an ionic bond. It has to be covalent. Absolutely. Now we got to share. So how many electrons do we need to share to make this atom as stable as possible? 2. Because this guy here needs 4, but this guy only needs 2. You can only share 2. You can't share 4. So he's out of luck. He's not going to be as stable. But we can share 2 electrons here. Which also means we can share 2 electrons here. And now, is this a perfectly stable molecule? No, it's not. But that's all we're drawing because I'm done. So this happens to be carbon, this happens to be oxygen. And when the 2 of them bond, since they have shared 2 electrons with each other, we would draw a double bond between them. Okay, so we could draw it like that, or we could simply draw it like this, or we could do this. Now, looking at the size of both atoms, and I drew them pretty well this time, would you guess that this is a polar covalent or a non-polar covalent bonding? Non-polar? Non-polar. Well, are these molecules, or excuse me, are these atoms super different in size from each other or fairly similar in size?
Fairly similar.
They're fairly similar in size, and when they are, you're talking a non-polar covalent bond. When one atom is much bigger than the other, you're going to be talking a polar covalent. So watch. So let's look at these 2 atoms here. Obviously, neither one of them is stable because this one is missing 2 electrons. This guy is missing 1 electron. So we can't form an ionic bond, right? Can we form an ionic bond? No, we can't. So we're going to share. What's the maximum number of electrons we can share?
1.
1, absolutely. Now this electron here, look at the amount of time it's spending in its own orbit compared to the orbit of that atom. This one's much larger. Same thing here, we're going to share this electron, but it's going to spend much more time around this atom, which happens to be oxygen, than it is around hydrogen. Yes? So what kind of covalent bond would you say this is?
Polar.
This is a polar covalent bond. Now is this a stable molecule? No. So let's bring in one more hydrogen. Now, is this a stable molecule?
Yeah.
Yes, absolutely. And of course, we could also write this like this, or like this. And of course, you know, this is water, yeah? Now, remember I told you that if an atom is stable, it doesn't want to bond to any other atom, right? Well, the same thing with molecules. If a molecule is stable, it doesn't want to bond to anything else, any other atoms, any other molecules. And if an atom is stable and doesn't bond to anything else, or if a molecule is stable and doesn't bond to any other molecules, it's a gas. Okay? This also means we have a little bit of a problem here. Because didn't you tell me that this was a stable molecule? Yeah. Look at it. Is this a stable molecule? I love how students all of a sudden question their own judgment when the teacher says something like that. Is it a stable molecule? Heck yeah, absolutely. You were 100% correct. It is definitely stable, which means we're screwed because I can't have ice cubes now. Because for something to become a liquid or something to become a solid, molecules have to bind to each other. So a molecule of gas is floating around separately all through the air. But if I want to turn it into a liquid, I've got to get multiple of these molecules to start binding together to form a liquid. And in order to form a solid, I've got to get these liquid molecules to pack in really, really close to each other to get my ice cubes. But if this water molecule is totally stable, how the heck do we get it to bind to other water molecules so that we can have liquid or solid water? Hydrogen bonding. Okay, well, let's take a look at that because that sounds totally correct to me. So if you look at this molecule, and one of the things I want you to take a minute and look at are the electrons. And this guy has 2 electrons. This guy has 8 electrons, officially now, right? Okay. But notice the electrons spend way more time around this oxygen than they do around this hydrogen. Now, when we started out, okay, you told me that oxygen has 8 protons, 8 electrons. Okay, so I'm just going to write that up here. 8 protons, 8 electrons should have an overall 0 charge. But if each of the electrons from hydrogen spends the majority of their time around oxygen, it officially doesn't actually have only 8 electrons anymore. It officially has 10, okay? Which means that this oxygen isn't really a 0 charge anymore. It's not really neutral anymore. It's really kind of sort of negative now because it has so many more electrons to it. And so we put this little kind of squiggly sign here that says that oxygen is now partially negative. Which also means that the electron from hydrogen spends most of its time now hanging out with oxygen, which means that we started out with 1 proton and 1 electron and an overall 0 charge. But what charge, if the electron is spending most of its time with oxygen, does our hydrogen have? Most of the time, it's slightly positive. So if I bring in another water molecule that is slightly negative and slightly positive, look what has the potential to happen. It's almost like it's ionized. And our oxygen and our hydrogen can bond to each other. Now, notice I did something a little different here. Okay, see the solid lines for the binding between the oxygen and the hydrogen within the water molecule? Those indicate that these are polar covalent bonds. But this dotted line between the oxygen and the hydrogen between the water molecules, this is not a really strong bond. It's a pretty weak bond, but it's what we would also call a hydrogen bond. Okay? Now, we do a lot of hydrogen bonding in the human body. Way more than we ever do covalent bonding, which is really kind of interesting. Because we're mostly made up of carbon, hydrogen, oxygen, and covalent bonds usually have carbon, hydrogen, and oxygen in them. But we do a lot of hydrogen bonding. So there's a few things I want you to know about hydrogen bonds, because we're going to use this over and over again. First of all, the reason I did a little dotted line that you need to know is that hydrogen bonds are weak bonds. They're very weak. And when you have a very weak bond, what it means is it doesn't take much energy to make the bond or break the bond. So very little energy is needed to make a hydrogen bond or to break a hydrogen bond. So, number one, hydrogen bonds are weak bonds. Takes very little energy to make them or break them. And the last thing I want you to know about hydrogen bonds is that they form very quickly and they can break apart very quickly. And that's going to be really important, especially when we start talking about proteins. Because bonding in proteins has to go really fast. So hydrogen bonds can form quickly and they can break quickly.